This time, let's now talk about another type of polyhedron, which are pyramids. So, a polyhedron that contains triangular lateral faces with a common vertex and a polygonal base is called a pyramid. So, as we can see here the base is a polygon, and then the lateral faces are all triangles which meet at a common point called the vertex. The polyhedron is called a pyramid. If the axis of the pyramid, this line segment here is the axis, is perpendicular to the base, then the pyramid is a right pyramid. Otherwise, the pyramid is said to be oblique. Now, the line segment is the axis, and the length of the axis is what we call the height of the pyramid. Then a regular pyramid is a right pyramid whose base is a regular polygon. So, when we say regular polygon again, it has congruent sides and congruent angles. Now, the important things that we need to know in the mensuration of pyramids would be, this is the height, while this is the slant height. The slant height is the height of each triangular lateral face, which is usually what we would need. Further, in the mensuration of pyramids, it's more common that we are given with regular polygons. That's why we would also need some facts in the mensuration of regular polygons. So, one thing, the central angle of regular polygons can be computed by dividing 360 by the number of sides. Again, this is for the regular polygonal base of our pyramid. Now, one important segment that usually we need to compute, especially for the slant height, is the apothegm. The apothegm is that line segment. Let's try here. So if we have a regular square, for example, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. There, if we have this square, from the center of the square down below, this line segment is what we call the apothegm. So the apothegm of a regular polygon can be given by this formula. S stands for the length of the side of the polygonal base, while N is the number of sides. Just like the one here, number of sides. There you go. And the area of a polygon, it can be computed by 1/2 times the perimeter times the length of the apothegm. That's why this is one other reason why we would need the apothegm. Further, the volume of a pyramid is 1/3 the area of the base times height, or the 1/3 the area of a prism. We don't have the time to show it here, but it can be shown that the volume of a pyramid is indeed 1/3 the volume of a prism. Now, let's work at some problems. First, a regular hexagonal pyramid, this one here, a regular hexagonal pyramid has one lateral edge which measures 10 centimeters. The length of one side of its base is 6 centimeters. And we are asked to find the altitude, slant height, total surface area, and volume of the pyramid. So, let's first draw a regular hexagonal pyramid. That's number 1. So, a hexagon, I'm just going to guess estimate our length. So, it might not look like actually regular because I'm trying to make it look flatter. Oops, there you go. Let's oops. Okay. Then we shall have one common point for our vertex. Let's assume that we won't pass that in there. Here, here, here. There you go. So we have our hexagonal pyramid. Oops. Here. Our hexagonal pyramid has one lateral edge which measures 10 centimeters. So one of these lateral edges here, this measures 10 centimeters. And the length of one side of its base is 6 centimeters, making the length of the other sides of the base 6 centimeters. We are now asked to find the altitude, slant height, total surface area, and volume of the pyramid. Well, first, let's look for the altitude of our pyramid. So the altitude would be from here, from the vertex down below here to the center of our base. Now, one thing to look for the height, we can use some other segments to find the length of that base. What we're given is this, the length of the side, and then here. We can make another, or we can make other line segments that maybe we can easily find the measure so that we can use that to find what we need to find. So here, to find the height, we can use this. Why? This is already forming somehow looking like a right triangle here. All I need is this line segment. Since the lateral edge is on the corners of our hexagonal base, then we need the length of the side. The question is, can we compute that? So if we're going to try and make the hexagonal base, oops. Okay, a good estimate of a regular hexagonal prism. The hexagonal base. We need from the center this line segment. So I'm going to assume this one here. This line segment here. The question is, how do we get that? It's not the apothem, because the apothem is actually this one here. Or let's just make it straight. Here towards the center of our base. So maybe we can turn both around so that it's easier for us to view. Let's place the apothem here, while the line segment that we're looking for is this one. Now, looks like what we have here is a right triangle. The question is, how can we find the measure of that side? Now, what we can do first is find the measure of the apothem. And the measure of the apothem is given by this formula here, this one here. So that would be the length of the side. Let's write the formula first. The length of the side all over 180. Let's double check that. Two first. Twice the tangent of 180 divided by the number of sides. The number of sides. Yeah. In this case, this becomes the length of the side is 6 divided by 2 times tangent of 180 over coincidentally 6 sides as well. So, with that, I am going to get 6 over 2 times tangent of 30 degrees. And we know the tangent of 30 degrees is square root of 3 over 3. So that's 6 times 2 times square root of 3 over 3. And therefore, this becomes 6 over 2 square root of 3 over 3, which will become 6 times 3 over 2 square root of 3, which becomes 9 square root of 3. Rationalizing it, I'm going to get 3 square root of 2. So this apothem here measures 3 square root of 3 centimeters. But the question is, how do we get the measure of this side? Apart from this, we can also get the measure of the central angle. So if we form another This one here is the measure of the central angle. And the measure of the central angle theta will be equal to 360 divided by 6. This is equal to 60 degrees. 6 because 6 is the number of sides. Now, the apothem is here in the middle. It's on the midpoint of each side, which also tells us that the apothem bisects the central angle. Therefore, if the entire central angle is 60, then this angle is 30 degrees, and this small angle is also 30 degrees. With that, we can now get the measure of this side. Because the measure of this side looks like a hypotenuse, and using this and this length, I can get cosine of that. Cosine 30, then we get the length of that line segment. Thus, this will then become the cosine of 30 degrees is equal to the adjacent side, 3 squared of 3 over h, which is this line segment here. Cross multiply, I'm going to get h cosine 30 is equal to 3 squared of 3. Dividing both sides by cosine 30, h will be equal to 3 squared of 3 over, we know that cosine of 30 degrees is square root of 3 over 2. So this becomes 3 square root of 3 times 2 over square root of 3. This gets cancelled and we get 2 times 2, which is equal to 6. Which now tells us that the measure of that side is actually 6. This is 6 actually. Also, this is 6 centimeters. Let's raise that up. I apologize for the messy solution. Should have written it down below, but I'm aiming for us to see the solution here. So now that we know that this is 6, we can now compute for the height. Should have used a different variable, but anyway. So now for the height h, going to move it to the side here. There we go. The height h, this should have been h sub 1. So I'll make it h sub 1, h sub 1. So now height h will then be equal, this looks like a right triangle, but because it is, using the Pythagorean theorem, this now becomes h squared plus 6 squared equals 10 squared. The lateral edge being the hypotenuse of the right triangle formed by h sub 1, this line segment from the center of the base to its corner, and then the altitude of the pyramid. So it becomes h squared plus 6 squared equals 10 squared. So h squared will then be equal to 10 squared minus 6 squared. This is equal to 100 minus 36, which will be equal to 64. 64. And getting the square root of that, h will then be equal to positive or negative 8, but since we're talking about measurements, h is equal to 8. Therefore, our altitude is 8 centimeters. We are going to write that in some millimeter on. Now that we got our height and altitude, let's now get the slant height. The slant height, I'm now going to use a different color. The slant height now is the measure of the height of the lateral face, which is, it's not seen here, I'll just use this one. Here. Now, the concept of how we form a right triangle from the lateral edge, the altitude of the pyramid to this line segment can also be used, the same idea can be used in finding the slant height. In this case, what we can use instead is the height of the pyramid, the apothem of the base, and then the slant height as our right triangle. Maybe it's better to illustrate here. If this is the slant height, I'm going to use cursive L for the slant height, and then this is the apothem. There you go, it's the apothem. That would be the other right triangle that we formed, making this and making the altitude of the pyramid and the apothem as the legs, and then the slant height as our hypotenuse. We already got the measure of our apothem, which is this one, 3 square root of 3. So therefore, just forming out, writing the solution for the slant height. The slant height L, that's will be formed with the Pythagorean theorem. L squared will be equal to the square of the altitude plus the square of the apothegm. L squared will then equal to the height or altitude of the pyramid, which is 8 squared plus 3 squared of t squared. This becomes 64 plus 27. And 64 plus 27 gives us 91. And the square root of this is, well, square root of 91. We don't get the negative value because we're on mensuration. We forgot this is centimeters if I am not mistaken. This is centimeters, so we need to place the units. Height is 8 centimeters, slant height is square root of 91 centimeters. Now that we got the altitude and the slant height of our pyramid, we now get the total surface area. The total surface area of our pyramid would be the area rather of each lateral face plus the area of the base. Now there are 1, 2, 3, 4, 5, 6 lateral faces because, well, there are 6 lateral faces, so we get 6 areas. So yeah, we'll just use LA for the total lateral area. So we know the slant height and the area of each base, so we can use the formula 1/2 base times height, then multiply it to 6. So the 6 lateral faces times 1/2 times the base of our lateral face, which is 6, times the height, which is the slant height, which is square root of 91, plus the area of the base, a regular hexagon. We can now use the formula for the area of a regular polygon. That's 1/2 times the perimeter times the apothegm. The apothegm is square root of 3/3. What about the perimeter? Since all sides of this hexagon is 6, you just need to multiply 6 to 6. And that will be 36. So this is what we get. Now let's simplify things. So 6 times 1/2 times 6 times square root of 91 will give us 18 square root of 91. The other one, that's 1/2 times 3 square root of 3 times 36 gives us 54 square root of 3. Therefore, our total surface area is actually equal to 18 square root of 91 plus 54 square root of 3 square centimeters. Again, the 1/2 is from the area of a triangle. This is the base 6, and the height of the triangular face is the slant height times 6 because there are 6 right triangle. There are 6, not 6 right triangles. 6 triangular lateral faces. The area of the base is the area of a regular polygon. That's 1/2 times the perimeter times the apothegm. Finally, we go to the volume of the pyramid. The volume of the pyramid, here, the volume of the pyramid is equal to 1/3 the area of the base times height. We already got the area of the base, which is 54 square root of 3. So we get 1/3 times 54 square root of 3 times the height of 8 centimeters. Multiplying this, we get 1/3 plus 54 square root of 3 times 8 will give us around 54 times 1/3. It's actually 18. It's 18 square root of 3 times 8. So 8 times 18 will give us 144 square root of 3. Therefore, the volume is 144 square root of 3 cubic centimeters. And we have the box answers for our altitude or height, our slant height, our total surface area, and our volume. And within this problem, we're also able to show how we can find the apothegm, the central angle, a perimeter and area of a regular polygon because, well, the regular polygon is the base of the pyramid of this specific problem. So, the counterpart of a pyramid on curved surfaces is a cone. So, a conical surface is the surface generated by a straight line moving along a fixed curve and passes through a fixed point called the vertex not on the curve. So, for example, if this is your straight line, and then you have your fixed point here, once it moves along this curve, so it will go something like this. So this surface here is the conical surface that we were able to have. That. And if we have a circular base, then we have what we call a circular cone. If the axis or the height is perpendicular to the circular base, it's a right circular cone. Otherwise, it's an oblique one. Now, the total surface area of a right circular cone is composed of this lateral surface area opening up, having this formula pi RL for the formula of its area. So the total surface area is this area plus the area of the circular base, which is pi r squared. While the volume of a cone follows the idea that the volume of a pyramid is 1/3 the volume of a prism. In this case, though, the volume of a pyramid is 1/3 of a cylinder. And the volume of a cylinder is pi r squared h. So we get the 1/3 of that, 1/3 pi r squared h, to get the volume of the cone. Now, let's solve a problem. Let's solve some problems regarding cones. So we are told we have a right circular cone with an altitude of 25 meters and a base diameter of 10 meters that rests on top of a right circular cylinder of the same base and 30 centimeters high. So we don't have just a cone, but we have like an entire figure composed of two splits. We have a right circular cone. Let's draw our right circular cone here. Let's assume that. Then we draw our somehow circular base. Circular base. That's one more. There you go. It tells us that the altitude of our right circular cone, this altitude is 25 centimeters and the diameter is 20 centimeters. This diameter is 20 centimeters. It rests on top of a right circular cylinder. So let's form our circular cylinder here and here. It has the same circular base because it rests on top. There you go. So we have this. And this cylinder is 30 centimeters high. So from there, that is 30 centimeters high. So first, we're asked to find the lateral area and the volume of the cone. So the lateral area of a cone is given by pi RL. The thing is, we don't know the radius and the slant height of our cone. Let's draw our cone only here. There you go. What we do know is that the height of the cone is 25 centimeters and its diameter is 20 centimeters. With a diameter of 20 centimeters, we can easily figure out that the radius is 10 centimeters. And as you can see, we already have formed our right triangle, the radius, the altitude, and here the slant height of our cone. So the slant height L will get involved with the Pythagorean theorem of this one, of this right triangle form. So that's L squared is equal to 25 squared plus 10 squared. 25 squared is 625 plus 10 squared is 100, so this becomes equal to 725. Therefore, getting the square root, L is equal to 5 square root of 29 centimeters. It's a bit difficult of a number to work with. Yeah, L is 5 square root of 29 centimeters. And now that we get the lateral area, we now have to find the volume of our cone. Let's move a little bit this for space. So the volume of our cone is 1/3 pi r squared h. Well, we have 1/3 times pi times our r, that's 10, so that's 10 squared times the height of 25. Therefore, we're going to get 1/3 times pi times 100 times 25. Thus, the volume of our cone, we did not get the lateral area on top. Let's first finish the one of the cone. So therefore, the volume of our cone would be 2,500 pi over 3. This is cubic centimeters. I apologize, I forgot to compute the lateral area above. So the lateral area of the cone would be equal to pi times the radius of 10 times the slant height of 5 square root of 29. Therefore, the lateral area becomes 50 pi square root of 29 square centimeters. So those are the mensurations for the cone. Now, we are now asked to find the total surface area and the volume of the composite solid. Let's move up again. So the total surface area, I'm going to use color blue. The total surface area now of this solid is the lateral area of our cone, and then the total surface, the lateral area also of the cylinder, plus just one base of the cylinder. Why is it not just total surface area of cone plus total surface area of cylinder? Because this circle is not part of the surface. So we remove that. So that's not the total surface area of both the cone and the cylinder. It's only the lateral area of the cone, the lateral area of the cylinder, and one base of our cylinder. So we already got the lateral area of our cone. That would be 50 pi square root of 29 plus the lateral area of our cylinder, which we get by, that's 2 pi times the radius of 10 times our height of 30 plus the area of our base, the area of this base, which is equal to pi times 10 squared. Therefore, I am going to have 50 pi square root of 29 plus 600 pi plus 100 pi. 30 times 10 times 2, that's 600, and then 10 squared is 100. Therefore, the total surface area that I will get would be 700 pi plus 50 pi square root of 29 square centimeters. So in the surface area, we have to be careful. But in terms of the volume, let me remove this X mark here. In terms of the volume, we don't have to be that careful. Because volume is volume. This space here and this volume here. So the volume of the entire solid is the volume of the cone plus the volume of the cylinder. And the volume of the cone will be equal to 1/3 times pi times 10 squared times the height of the cone, which is 25. For the cylinder, that's just pi times 10 squared times its height of 30. So, for the cone, we get the value of 2,500 pi over 3 plus 10 squared times 30, we get 3,000 pi. So, we can actually add this, and we're going to get the value of 11,500 over 3 pi cubic centimeters. This is the volume of this composite solid. As you might have noticed, we did not just use the mensurations for a cone, but we can also use the mensurations of other figures if we have composite figures. When we say composite figures, it is composed of two different figures that we have studied. In this case, a cylinder and a cone. And the last solid that we're going to talk about is a sphere. A sphere is a three-dimensional solid bounded by a surface consisting of all points equidistant from an interior called the center. Here, for its mensuration, we usually only have the surface area of the entire sphere, which is 4 pi r squared, and its volume, which is 4/3 pi r cubed. Some of the parts of the sphere that we can take note of is the radius, the diameter, and then the circle that contains the center is what we call the great circle. And half a sphere is what we call a hemisphere. So, we have here one problem regarding sphere. In number 1, the radii of two spheres are 4 feet and 8 feet respectively. Find the volume of a sphere whose surface area is equal to the sum of the surface area of these two spheres. So the first sphere, the first sphere, it's difficult for me to draw like a two-dimensional because it's drawn like this, has a radius of 4 feet, while another sphere has a radius of 8 feet. Please forgive the ugly book. So 4 feet and 8 feet. We're asked to find the volume of a third sphere whose surface area is equal to the sum of the surface areas of these two spheres. So, we know that the volume of a sphere is 4/3 pi r cubed. So we need the radius, which we can get from the surface area when we add these two spheres. Now, we are told that the surface area of the third sphere, the one that we're computing the volume for, is equal to the sum of the surface areas of these two spheres. And these two spheres, we compute the surface area as such. The first one, that's 4 pi then 4 squared, while the other one is 4 pi times 8 squared. So 4 pi times 4 squared gives us 64 pi, while 4 pi times 8 squared gives us 256 pi. Adding those two, we're going to get 320 pi. And now to compute for the radius, since the surface area of the third sphere that we're actually looking for is 320 pi square feet, 320 pi will now be equal to 4 pi r squared. So we divide now both sides by 4 pi so we can get the value of r squared. So this will then become 80. Getting the square root of this now becomes r is equal to 4 square root of 5 feet. We don't get the negative value anymore. With this in mind, we can now compute for the volume of the third sphere, which is 4/3 pi times 4 square root of 5 cubed. And therefore, we get it like this. 4 cubed is 64, while 5 square root of 5 cubed is 5 square root of 5. And I don't think we can simplify this. All we can do is multiply 4, 64, and 5 square root of 5 and have it with a denominator of 3. This now gives us 1280 pi square root of 5 over 3. So therefore, the volume that we're looking for is 1280 pi square root of 5 over 3 cubic feet. And those are sample problems of mensurations of pyramids, cones, and spheres.